So today we will see the CFD analysis of single turn pulsating heat pipe. This is a geometry which has been prepared with ANSYS design modeler. Now we are going to apply the boundary conditions. We are also going to produce mesh. So before proceeding, we'll just check out with the geometry how the geometry will be proceeding for our case. So I specified this as a air, this one as a water. I'm using water as a working fluid. This is a portion of air over here. So in all the cases you have to ensure that this is fluid over here, here also it is fluid, here also it is fluid, and lastly here also it is fluid. If by mistake if somebody has specified solid, in that case the errors will occur. So these are the few things that you have to remember. You may do the slice operation in order to select the suitable filling ratio for a given pulsating heat pipe. So as of now, say if I select all these three objects, say for example this one and this one, and I say if this is the portion where the fluid has been filled, the volume is 621.09 millimeter cube. So how to calculate the filling ratio? So that can also be understood from this. So simple way to do this is open your calculator. So right now this is the volume which we are having is 420 millimeter cube, and this one is 621 millimeter cube. So if I just take 420 plus 621 millimeter cube, so that comes out to be 1041 millimeter cube. So if I divide this 621.09 to 1041, so 621.09 divided by 1041, so in that case I will get a filling ratio. So if approximately it is around 61% of the filling ratio it can be selected. So how this can be done? You have to slice the geometry and accordingly you can proceed with the given filling ratio. You may change it to 70 or you may change it to 80 also, depending on that you have to slice the geometry accordingly. So this is how the geometry has been prepared. So next thing, we'll proceed for preparing the mesh, where we are going to specify heater zone and we are going to specify the condenser zone. The condenser area should be greater than the evaporator area, so that there will be the evaporation and condensation process that is taking place. So first I'm going with the analysis system. So you have to go with the fluid flow Fluent option. Just drag this in front. Now in front of mesh you are not observing any right click over here. So first of all, in front of the geometry you are observing right click. You can go to your workbench window and you save the work also, so that will be useful for us when we are again resuming this work for after some period of time. So let's save this work. Say for example with a different folder I'm going to have, say 99. Okay, so this is the folder which has been prepared. Now in that case I will specify the name, say for example single turn pulsating heat pipe. Okay, so you have saved this, so you can easily access this work later on. So as this process required a long time as far as the iteration process is being concerned, so that's why it is always better to save the work which is in progress. So first of all I will click on the mesh. So as per what the geometry has been prepared, we have to specify this as a portion of condenser. This one okay, this as a portion of condenser, this as a portion of heater, and this will be the filled with the fluid. So accordingly we'll proceed for meshing. So right now in front of mesh you are not observing any right click. So the green right click it will be there when you are generating the mesh. So we'll just click on generate mesh. Now in this case, computer at its own will generate the mesh. So this is one thing which you can do, or simply you can modify your mesh as per the requirement. So right now let's go for the statistics. So it shows somewhere around 80,000 nodes and somewhere around 70,000 elements. So as far as the student version of ANSYS has been concerned, we can reach up to 5,12,000 nodes. So if you want, you can reduce the element size also in order to have a better accuracy with your result. You can reduce this value. Say for example, I will take 0.001. Just check it out how many number of nodes and element right now we are having. Once I update this value, we'll just check whether there are increase in number of nodes or decrease in number of nodes. So here it was same, it was showing. So I will just try to increase this value, say for example 0.0001. If I take this and just try to make it update, we'll just check it out, the number of nodes and element which are coming over here. So if you are taking the fine mesh, there are likely to have more time for generation of mesh. So let's check if this value comes out to be less than 5,12,000 nodes. In that case we can proceed with the value, or if this value comes out to be more than 5,12,000, so in that case we have to reduce the size of a mesh. I will just check. Okay, so it is so quite bigger value. So taking 0.001, it 0001, it will give error in terms of student version of ANSYS. So that's why, and also this is limitations are up to 5,12,000 nodes. So I will just try to reduce this value, say for example 0.009. I will just check with how the number of nodes and elements are there, and accordingly we'll make some modification. So let's say 0.009. Okay, make it update. Okay, it shows somewhere around 1,03,55. You can further change this size. Say for example I will take 0.0002 and we'll try to generate the mesh again. You will see 3,74,692. So right now the value which was taken is 0.0002. You can take some value which is 0.0001 to the value which is 0.0002. So some intermediate value can be taken so as to get the within the limit of your version. So say if I take 0. And try to generate mesh, this value should be less than 5,12,000 nodes. So if this is coming out less than that, we can surely proceed for the analysis. We'll just check it out, this value. So it shows somewhere 8,69,200. So whatever we have taken earlier, like 0.0002, that was okay. Somebody can go with, like we have taken 0.15, you may take it 1789 like that, and just check it out with what the number of nodes and elements you are getting. So right now I will proceed with the mesh size which is available here. So the node 3,74,692. So we'll proceed with this value. You can just check it out, the mesh on each of the cases. So now next thing will be to specify the heater and condenser. So this is a phase which I am selecting. Go to the create name selection. So specify here as a heater, or you can specify as an evaporator. Then this is the condenser part which you are having, where the heat rejection will take place, so you can specify this as condenser. Okay, so these are the two things which you have specified. One, it is heater, then we have it is a condenser, so you can just check it out whether you have correctly entered the values or not. So this is a part which is related to your mesh. You can go on to make it update, so that you will see the message that is mesh translation to Fluent successful. In that case, again you go back to the workbench window and check it out. In front of mesh you have right click, so you can proceed further for the next operation. So this is how the mesh has been generated. Name selection has been done. Now if you want, you can close the window over here for mesh. Now next thing is your setup. So here once you click on edit, so you select double precision. So depending on whatever the number of processes your computer simultaneously can run, you can specify that value. Sometimes if you entered more than the computer that we can say supports, in that case you might get some error warning when you are opening the Fluent window. Say for example I specified 10 over here as an arbitrary value and click on start button. If it supports to my version, okay, so here it shows the number of processes that can be used is student version, so not enough HPC parallel licenses, so you can go on to exit option available and just modify the things which we have specified earlier. So earlier I specified 10, now I will just specify only 4 and will start the option. Now if I do that, the next window when it will open, it will not show me any kind of error the way it was shown earlier. So now I can start proceeding with the simulation. So this is the thing which you have to remember when you are proceeding. So first thing will be to visualize the thing which are the object as per the requirement. So we have to select the transient model, then the gravity has to be specified in the negative direction of y. So we'll specify this is minus 9.81. okay. Now next thing is you have to select the model. So we are going to select the multiphase model, volume of fluid. Okay, make it apply. Number of phases you can specify. Then you can close this first version. Next one will be energy equation. We have to make it on. Make it okay. Then you have to go with K epsilon. Then enhance wall treatment. Then you have to click on thermal effect. Then you have to go with the curvature correction. So make it okay. So these are the few things which we are done in terms of the model. Next thing will specify the material. So go to the create. Now you can directly take it from Fluent database, or you can enter your values also. Sometimes we have some binary fluid or we have some mixture of fluid. In that case you can enter your properties over here, but the default material can also be utilized wherever they are available. Say for example water liquid and water vapor, which I want, make it copy, then close this. So close again this as a window. You will be observing water vapor and water liquid. So close this window. Now you required a material which is for your solid, so go to create edit. Now in that case you don't require aluminum, you require some other material. So go for the Fluent database, select the solid option. So whatever you want, say for example I want copper, so make it copy, then close. Again, if you are having some different material, you can enter your own values also. So make it close. So you can see water vapor, water liquid and copper aluminum like this. So material has been there. Now next step will be to proceed with the cell zone condition. Here we are applying some operating conditions. Say I am entering here as 4000 value, say for water, which is at, if it boils at 30 degrees Celsius under pressure. So in that case I have specified this value. Now next one is boundary conditions. So where we are applying the boundary conditions, accordingly we are going to proceed. So before proceeding to that, again I am going back to model. Over here the number of phases which I have specified 2. Now primary phase I will specify as a steam, that will be water vapor. Make it apply, you will see that change. Now next thing will specify the secondary phase as water, so specify it as water liquid, make it apply, you will see the change as takes place. Now next thing is phase interaction, so it will be surface tension 0.0736 that per, so this one wall adhesion over here. Next one you will have to specify the heat transfer mechanism, so we are selecting it from water to steam. So evaporation, condensation, say at what temperature, say for example at 303 Kelvin if the water will starts boiling. So make it okay, make it apply and close this window. So we have applied the number of phases, we have specified the evaporation, condensation back into the phases. Now go to your again the boundary conditions which are having available here. So here I will specify the contact angle as 20. No changes in the temperature for the condenser, only at heater I am going to apply a certain temperature. Say for example here if I apply say for example 343 Kelvin, make it apply and then close. So this is for your heater. Similarly we have to apply the boundary conditions at each and every place where I will specify this as a 20. I'm not going to change any kind of temperature on the other cases. So here also not making any changes, we'll just specify the contact angle over here, that is 20. Close, again we'll have one more contact angle over here, it's 20, make it apply, close. This is also, so ensure that each and every case you are specifying the contact angle, that is 20. So this is 20, close, this is also 20, make it close, make it 20, okay. So we have applied the contact angle at each and every place. Now close this window. Now so next thing will be we have applied the boundary conditions. Let's proceed for your initialization. Now in that initialization I will keep this as it is value, then start from initialization patch. Now you have water volume fraction, I will specify here it is 1 and will patch with the zone which is water. So click on patch and then close, then go to calculation activities. So this is useful when if you want to save the work during the case of power failure. Then solution animation, you may specify the solution animation here. So in that I will select a phases, volume fraction of say water, and we'll just click on the wall, so everything will be getting selected. Now in that case I will select float one and make it apply. So we'll close this and click on so here you can specify water liquid, make it click on save display and you can close this. Now click on this, you can see select the particular view, say for example front, and make that okay. So you can specify the name also here as animation. then go to run calculation. So instead of fix, I am going to have adaptive, say for example 500 at the initial stage. So here I am taking 0.0005 so as to avoid the problem of current number. Now what I will do is I will start with the calculation. So once you click on, the iteration process will start. So let's proceed. So we have started the process of iteration over here. So this process will take time, and as we have set the animation, you will be having one more window where you will be able to see the actual progress of your simulation. Means whatever iterations we are running, you will be able to see the temperature where it has been applied, and the fluid which is there, like a liquid, has been transformed into vapor. So that visualization can be done when the iteration process is been going on. So based upon that, you can predict the things, whether you are going in the right way or not, whether you are getting the right pulsating action or not. So these things can be guessed if you set the animation over there, and that is useful when you are running the simulation, because the simulation may last for we say a long time. So you don't want this thing that we can say after completing iteration you come to know that this is not going in the right way. So this is always a better practice to set the solution animation, so that while the iteration process has been going on, you will be able to visualize the things on screen. So we'll just wait for some time so as that the iteration process will complete. We have specified the number of time step as 500 and the time step size as 0.0005. You may reduce this size also, but sometimes the problem of current number can take place, and that may further leads to the interruption in the iteration process, and the iteration process cannot be restarted again. So that is one disadvantage if the smaller time steps has been selected. So the time step selection should be done carefully, so that there will not be a problem of current number. At the same time, we also need to ensure that the time required for the process, it should be a minimum. So balance has to be maintained between the time step which you are selecting, and at the same time you want to avoid the problem of current number. So these are the things which need to be remembered. Now you might observe some small changes in the portion over here. So that is actually the liquid that has been transformed into a vapor because of the heat which has been applied in the evaporator section. So we'll just wait for the iteration process to complete, and then we'll check how the variations are there throughout this. You may zoom in to visualize the things, whether they are going in the right way or not over here. So definitely if you are taking the finer size of the mesh, it will be very we say the results should be in the proper direction if you are taking a fine mesh. Now let's see how the process has proceeded. Now you can see this is the iterations are completed up to 12%. So we haven't yet completed to the full extent, but at the same time what we can visualize at the bottom is the formation of vapor bubbles, which can be seen over here. Again, the process is not the fully developed, so after some iterations you might be able to visualize this in terms of alternate liquid and vapor slug, but right now it is not there. But the process has started, the vapor formation has started, so this can be visualized with respect to your animation which was set. So that is useful when we are running a simulation like this, where the simulation can last for a long time. So in that situation, it is very helpful. Whatever we have done is going in the right way or not, to check that the setting a simulation is very important. So right now it is only 12%, 13% has been completed. We will check it this whole process once we have some alternate liquid and vapor slug.